Faris from University of Arizona. The title is Rosetta Stone, Combinatorics, Physics, and Probability.
Thank you. Well, everyone knows about the Rosetta Stone. It was discovered by Napoleon's expedition in Egypt, and it had an inscription in 3 languages. 2 of them were Greek, and 1 of them was the Egyptian hieroglyphics. And so it was the key to figuring out the connection between what people knew and what they hoped to know about hieroglyphics. So this talk is a little bit in the same spirit of trying to make some connections that are actually fairly easy to make, but I think have not always made it to the center of attention. So let's see if I can move right on. I want to talk about 3 things. One is combinatorics. That's topic 1. Second is statistical mechanics, equilibrium probability systems. And what I want to do is say things about combinatorics that you've already mainly heard. And I want to say things about statistical mechanics that you've already mainly heard. But what I want to do is argue is that they're exactly the same. Not analogous, not almost the same, not suggestive of each other, but precisely the same. And the third part of my talk is about some recent work I just did, which is related to the Fernandez-Procacci result. But the good news is I think I won't get to it. So
we should leave now.
There's something to learn here. All right. So actually, the main message that I have is on this first slide. And it's the notion of colored set. So let me give an example of a colored set. So let's say we have point A, B, C, D, E. So these are what are called labels. So this is a set with 5 points. There are 5 labels. Doesn't matter what the labels are. And then you have a palette of colors, and you color these sets with these various colors. Let's see if I can do it. So you might have a couple of green ones, and a yellow one, and a blue one, and a red one. So that's a colored set. And in Labelle's very first talk of the conference, I was waiting with great anxiety to see if he would mention colored sets. And I kept thinking he was going to do it, and he never quite got to it. And that is the missing key to what's going on in this business.
This is just a name for a mapping from one finite set to another.
That's quite correct. And that's what I have, of course, written up here. A colored set. You have a fixed set of colors. So this set is going to be fixed once and for all. Fixed set of colors. And it's a map from the index set to the set of colors. Now notice, there's a notion of isomorphism of colored sets. 2 colored sets are isomorphic if you can map the index sets keeping the same colors. Okay? So that is the key notion. Now once you have a colored set, then you can define this multi-index or occupation number function, which just counts how many times each color is assumed. So here we have red is assumed once, blue is assumed once, green twice, and yellow once. So that's all there is to the notion of colored set. Now, why does this first slide contain the secret? It's because this also has an interpretation in physics where the colors are, see, we had 4 colors, red, yellow, blue, and green. And we have the particles. Let's see, we had I can't see the colors from here. We had a yellow particle, and the B and C were green. So the B and C are green. The yellow was A, the red was E, and the blue was D. And we could have other colors. We could have a purple here. So there's another interpretation of a colored set. And in this interpretation, the labels are particles. And the colors are locations where you may put no particles, one particle, or several particles. So that's exactly the setup in the equilibrium statistical mechanics of particles.
And here the particles are all considered distinguishable.
It's a set.
Is it extension of species instead of species on set, it's species on multi-set?
That's what we're coming to next, yeah. These are multi-sets or colored sets.
Yes, that's it.
Okay, so a species assigns to each colored set a corresponding weighted set. So that's the generalization that's in the book of the Canadians, and which they have whole chapters on, but which somehow never got mentioned at this conference, and that's the missing link. So let's give now, technically, if you want a technical definition of species, it's a functor from the category of colored sets to the category of weighted sets. That's a precise definition. Species has a precise definition. It's not one of these sort of vague notions that can mean anything you want. So let's look at an example of a species, okay? So first of all, let's assume that we have weights depending on the colors. So P and Q are two different colors, and for each P and Q there is a weight, T of P and Q. This was called capital F in Alan's talk, in Alan Sokol's talk, but I've gotten used to using T for, it's a kind of interaction between two colors. Now remember, in this case, the colors are locations, so it's an interaction between two locations. So here's an example of a species, the species of graphs. So for each colored set, we look at the set of all graphs. So we can draw some edges. So we look at all graphs, that's the weighted set. And each graph gets a weight, which is gotten by multiplying. You look at all the edges, and you multiply the weights for the edges. So that's the weighted set associated with the weighted set of all graphs over your particular colored set. So that's the basic definition that's going to make everything work. Are we all on board here? It's been a long week. Can you still focus? If I don't go too fast. Am I going too fast?
Not so far.
Not so far. Okay, not yet. Okay. All right. So let's go fast then. So the whole key of the species game is there's a transform. It's a little bit like a Fourier transform. The Fourier transform takes a function of time and gives you a function of frequency, which looks entirely different, but which encodes a lot of the information, or maybe all of the information in the case of the Fourier transform. So here, once you have a species, you have this exponential generating function. But unlike in the lecture of Lebel, where the functions were only of one variable, there is a different variable for every color. This is Alan Sokol's multivariate philosophy at action, at work. So we have, for each color, we have a variable. And so the exponential generating function has this 1 over n factorial. That's characteristic of labeled combinatorics. And then it has a sum over all the colored sets of this coefficient and these variables. So my generic variable I'm calling W, so that some people would call it X or something like that. And then the coefficient here is the sum of the weights of all the things that the species has generated. So in the case of the graphs, it's the sum of the weights of all the graphs. And in the case of graphs, you can write a slick expression for the answer. because you don't see any graphs here, but if you expand this using the distributive law, you get, as we've seen in this conference before, the sum over all graphs with that given all edges with that given vertex set. All sets of edges with that given vertex set. So that's the story. Let's move on. Now here's something that's confusing in this whole business. You can write everything in two different ways. You can write it the way I just wrote it, where I did some sum over colored sets. But you can also write it just like you'd ordinarily write a power series in many variables using multi-index notion. And these are entirely equivalent ways of writing these exponential generating functions. One is as good as the other, and their main role is to confuse you, because whichever one you're thinking of, the person you're going to be talking to is going to be using the other notation. So, but at any rate, these are, again, the same exponential generating functions, just written differently. Written with multi-indices instead of with these some.
Can you go back a second?
Sure.
Let's just look at it.
So
No,
there.
no, next one. G of W is sum of n, capital N.
So n factorial is actually the factorial of a multi-index.
N is a multi-index. This is a sum over multi-indices to say how many particles you have in each flat.
That's right.
In each.
Right. This, by the way, in statistics, in statistical mechanics, is the grand partition function that we've seen so many times in the discussion of particles.
And then the T is a vector.
Well, the T is
T is a vector which
it has two indices, but then you look at the you count the number of times that pairs occur. So
right.
that
You
so
can think
so
of T as having indices that are one element or two element subsets
right.
of the set of buckets.
Exactly right.
And then this is the interaction telling you how many pairs of particles there are interacting there.
Yeah, it tells you how many pairs of particles are. You might have two particles in one box, or you might have a particle in one box in the other box. I'm just writing this in this very compressed notation because there's always this trade-off. If you write things in a compressed notation, you get slick-looking formulas, which are incomprehensible. If you write things in an expanded notation, you get expanded-looking formulas, which are also incomprehensible. So it's just the thing we have to deal with all the time in mathematics anyway. Now, here are some examples of species. I'm going to take all of my species are going to be graph species. There are many, many other kinds of species, but because I'm trying to make this connection, I'm going to take graph species. So there's the species of all graphs over a given colored set. Here's its exponential generating function. There's the species of all connected graphs over a given colored set. And here's the exponential generating function for those guys. They're related by exponentials, as we'll discuss. There's the species of rooted graphs with a root of a fixed color. So in this context, when you look at a rooted object, that means taking the set of labels and focusing attention on one of the labels. So you pick one of the labels and you focus attention on it. You're only going to focus attention on green labeled objects. So this subscript here, P, is the subscript that indicates what color you're going to take the root, and you're not going to look at things with with roots of any other color. Now, in, of course, statistical mechanics, that corresponds to fixing a location as a kind of reference point, which is some people called pinning during some of the lectures, though I think pinning is slightly different. I can discuss the difference if you care, but another one is rooted connected graphs. There's trees. There are rooted trees with a root of a given color. So all this was in Lebel's talk, except he didn't have the colors. Now let's look at operations on species. I'm not going to go over this in much detail because Lebel did an extremely good job of explaining operations. But I want to distinguish between good operations and bad operations. Now, I may get into trouble because I have species experts in this audience, and they may not like my categorization of good and bad, but You speak up if you don't agree. So a really great operation, like stepping on somebody's transparency here. It's exciting. A really great operation is this convolution product. You take two species and you want to form a new species. So what you generate are, you look at all ordered pairs given by, well, first you break up the set of labels into two disjoint sets, who with intersection empty and with union the whole original set of labels. You break it up into all possible ways, and then you take an ordered pair consisting of something built over the first subset. That's a misprint. This should be V and this should be W. So I'm sorry for that typo. Let me apologize. So the U, you have the U, and you were supposed to break it up into a V and a W, and I wrote U and V. That's a mistake. You discover these mistakes right in the middle of lectures, of course. There's composition. Let me not spend a lot of time on this because it's a potentially time-consuming thing to explain, and LaBelle already did a good job of explaining it in the case without colors, and so let me not linger on it now, even though it's actually deserves about 15, 20 minutes of staring at it to get it straight. There's picking a root of a given color. That's a way to go from one species to another. So you could look at the species of connected graphs, but then you could look at also the species of connected graphs together with a root that's blue. Okay, so that's another construction that goes from one species to another species. Now, a bad operation is Cartesian product. Uh-oh.
It's not so bad.
Good, a sign of life at Friday afternoon. Oh, good. I think it's terrible. No, it's bad. It's very bad. It's very bad. It's very bad. I want to argue. I want to show you how bad it is, and then I'll see if you have any fight left in you. Now you can write down species equations. So here is one of the first famous species equation. This says that the species of graphs can be obtained from the species of connected graphs by composition with the species that simply recognizes sets. So that species, for each set, for each colored set, you simply look at it and say, good. You get one element for your construction with no weight, with weight 1. Sorry, with weight 1. So this says that every graph, you can partition the set into the vertex set into subsets, non-empty subsets, with a connected graph on each of the non-empty subsets.
Let me just, all of your species in this talk will be species over colored sets rather than the species over sets that...
with the possible exception of this one in that formula. Yeah. Basically, they'll almost all be over colored sets. One or two will be over just plain sets. Okay. Here's another combinatorial equation that rooted graphs are given by rooted connected graphs together with graphs. That means you take a graph, so some crazy graph like this, and you pick a root. So here's a root, and now you say what's left. You have a connected graph connected to that root, and then you have another graph left over on the complement. Here, rooted trees, a similar equation. And these equations, they're corresponding functions for the exponential, they're corresponding equations for the exponential generating functions. And notice these are pretty nice equations. It's because I only used good operations on the species.
What is E1P?
What?
E1P is the colored set of one element that's colored P and otherwise it's
E1P here says, look at a set. If it has precisely one element of color P, say yes, otherwise nothing. So it's recognizing the root.
Oh, I'm sorry. It could be on a set of cardinality more than one.
Right. It just doesn't
only one.
Only returns it only returns anything when the set has precisely cardinality 1 with color P.
Well, not singleton, what they call singleton.
So this is the singleton. This is the singleton of color P. Singleton of color P. It's picking a root of.
There were two interpretations, and I haven't figured out which is the right one. Is it that the set must be of cardinality 1 and that element must be colored P?
Correct.
Yes.
Oh, I thought you told me the set could have any cardinality of
No.
which only one element
No,
colored.
that's the E is the set can have any cardinality. The E1 can have only cardinality 1.
Okay, no, I thought there was a different notion, which was any set, but precisely one of the elements is colored P.
No,
No, that one.
that was never on the screen. I better go over. Better jump past this slide. It's causing trouble. Here are some more species equations. So here I am.
One like zero species, if it has a color.
What?
The one singleton species with the zero also. The zero species, same one or only one?
The zero species,
Colored
I
zero.
think, returns something only if you have the empty set, right?
Yeah.
Sorry, can you go back? I just want to see the last equation. I want to read the tree equation. Can you say in words? This
Okay, let
equation says
me say what the tree equation is. So you have a tree with a root of a certain color.
Yeah.
Okay. Now you have this big set. First you split the set into two parts. There's a one element set where there's the tree, and then there's the complement. So that's the multiplication that goes on right here. Okay. Then there's this exponentiation here, which says you partition the complement into disjoint sets, and on each of these sets you have a tree. And of course it could just be a trivial tree like that. And then you connect the root to these trees, and that's what the combinatorial equation says. It's the recursive equation for trees. It says every rooted tree can be gotten by picking a root, then partitioning everything else, and putting a rooted tree on each thing in the partition.
Right. Yeah, I knew that, but I don't understand the E1P.
This one here you don't understand? I'd like not to explain that because it's going to take a little bit of time and it's just not worth it. It's something to do with the weights. Okay?
Okay, but anyway, that gives the last function.
So this is the equation that you get. This is the standard equation for trees, which you do understand. This is picking the root. This exponential function is partitioning. This is the thing I don't want to explain too much. This has to do with the interaction. And here's the recursive thing where all these trees that occur here. Okay?
But all these things, P and Q, are colors.
P and Q are colors in the combinatorics notation or terminology, and they're locations in space in the physics terminology.
But generically, in physics, they would be called states.
They would be called sites or locations or places or polymers or God knows what.
Okay.
Boxes for putting.
Boxes. I like boxes. Okay. So here's some more species equations. These involve a bad operation, namely this Cartesian product. And this is the equation let me focus on this one. This is the equation for rooted connected graphs. And it says that if you take a rooted connected graph, you have a rooted connected graph. You pick a root. You have the root. Now the complement then breaks up into connected components because some of these things might only be connected via the root. So we're looking at the complement. So you have to pick connected graphs on this sets in this partition. But for each connected graph, you also have to pick a subset of vertices to which you connect. So you have to pick two things. You have to pick a connected graph plus a subset of vertices.
That's what PP plus means?
That's P plus means it has to be a non-empty subset for it to be connected to the root. So the P plus means non-empty subset, and this P is again some esoteric having to do with colors. It might even be wrong. I can get LaBelle to straighten me out on this. But it's probably close to
Okay,
right.
and then can you explain to us those equations in words?
Okay, which equations?
For three,
This one?
no, the three generating function equation.
Okay, so let's focus on the connected graph one because I want to try to move along quickly. So this one says that the generating function for connected graphs with a root of color P is given by selecting the root, then by partitioning the complement, and then this whole expression here is taking a connected graph connected together with a non-empty subset of vertices on each set in the partition.
And 1 plus TPW is shorthand for the vector 1
Okay, so
plus TPQ times W.
yeah, that's right. So there's really lots of WQs, and this is TPQ times WQ, because there are lots of variables in these multivariable. This is the multivariable philosophy, right? And then the minus CW here is trying to get rid of the empty set of. I mean, you need to connect everything, each thing here, to a non-empty set of vertices over in these elements of the partition. So this is an equation for rooted connected graphs, and it's presumably due to Meyer or to Meyer's ghost, or Meyer and their ghosts. But I don't know if they actually wrote it down, but it's something in the spirit of Meyer equations from the theory of gases. But it's not a closed form equation because here you have the rooted connected graphs. Here you just have connected graphs. But you can get a closed form equation at the price of doing one of these integral identities. So this is a closed form equation for rooted connected graphs at the price of having this integral. So the reason, this scaling operation is a pretty bad operation on species, and that's why I'm using the term bad, though apparently it's disputable.
And it's still bad with the integral.
Yeah, the integral is bad too, yeah. Oh, I mean, it's still bad with the integral. There's still the scaling in it. Yeah, there's still the scaling. The scaling has become even more complicated because it's scaled by different amounts.
But even though it's bad, you're going to use it.
Of course. Okay, now let me go on to the Katetsky price condition. We heard about conditions for the convergence of cluster expansions. So here's the equation for rooted trees with a root of color P. It's a closed form equation. It's a fixed point equation. It's phi of z equals z. There's another typo. I was supposed to write the fixed point equation phi of z equals z, and it looks like my finger hit the A button instead of the Z button, and phi of z equals z is what I meant to write. It's a fixed point equation. So z is here is the z, here on the left is the phi of z. The t is the z.
So capital T in that equation corresponds to the matrix of little t's in the other equation?
This is a vector of numbers.
Right, and then
Indexed
that vector is called z.
That vector I'm going to call z.
And then in the middle equation, the capital T corresponds to the little t of the matrix little t of the other equation.
That's right.
Okay.
Okay. Now here's a remark about fixed point equations. Take an increasing function from a complete lattice to itself. Now a complete lattice is a partially ordered set in which every subset has a supremum and every subset has an infimum. So take an arbitrary increasing function. Notice it doesn't even have to be continuous. It's an arbitrary increasing function. Then it has a fixed point. So what's the picture of that? Let's see if I can draw a picture of that. I'll draw a continuous function, but it doesn't have to be continuous. So here is an increasing function, and it has a fixed point. Here's the function phi. Here's the z-axis. An arbitrary increasing function has a fixed point. Now, of course, you could have this picture, but then the fixed point would be at plus infinity. And the plus infinity has to be a live option for it to be a complete lattice. And you can, not only that, you can get the fixed point by taking the infimum of this set. So a condition to have a finite fixed point is that this set has some finite vector in it. The Kotetsky-Price condition is that there's a finite vector in that set. So the Kotetsky-Price condition is a necessary and sufficient condition for the tree equation to have a finite fixed point.
Excuse me, what does it happen when you have many fixed points? You are taking the smallest of that?
Ah, good question. This is going to be something I'm going to try to pass over without anyone noticing. You definitely want to take the smallest fixed point, and you need to kind of use that fact at some point. Let me try and say as little as possible about that because I'm looking at the clock. Okay, but you're quite correct. You want the smallest fixed point. In fact, this prescription does give you the smallest fixed point. Let me skip this one because of time. Let me just say a word about other ways of writing equations of the Kotetsky-Price type, or Dobrushin type, or Fernandez-Prakashi type. If you write z equals phi of z, here I got it right. Write it as w times f of z, where w is this vector of parameters corresponding to the colors. You can write it by a brilliant change of algebraic manipulation this way. And so the Kotetsky-Price condition becomes that there's a finite x so that this inequality is satisfied. And we saw the equations written in this form a number of times during this conference. It's definitely the wrong way to write the equations because it's not at all obvious that such an equation has a solution. I mean, you say, well, it's obvious because you can draw the following picture. Let's draw a picture. Here is, let's see, I want to write z and w. So here's a w, and you want to look for a solution. Right? There's this bad solution over here, but you want this one, the least one. So it's obvious that this equation has a solution, but it's only obvious when there's one variable because you're implicitly using the intermediate value theorem.
But doesn't it follow from the slide that you skipped on solution by iteration?
Oh, it follows already follows from two slides before it. But I'm saying if you write it as a fixed point equation, it's obvious it has a solution. If you write it in this form, you start to worry about, is there some topological fixed point theorem I could use? It starts looking very difficult. I mean, you don't see that the Kotetsky-Price condition gives you an actual fixed point or an actual solution.
May I add a sentence? When I said, was it the smallest one and so on, you should have answered me, this is a lattice, maybe the smallest one is not defined.
No, there's always always a least fixed point.
Isn't it how you prove the Zorn's lemma using...
There's always a least fixed point, there's no question. Okay. Well, let's go to the physics. We have a little bit of time. I promised you physics as well as combinatorics. So again, the set of colors is a set of locations. This label set is a set of particles. A colored set is a particle configuration, one of these things. The Boltzmann factor is the generating function for graphs. The variables WP corresponding to the colors are prior weights for being at prior activity rates for being at different sites. We've seen that all many times. Probability model is you divide by the grand partition function. G must stand, does it stand for grand partition function or does it stand for graph exponential generating function? I'm not quite sure. But at any rate, this is the probability model for the occupation numbers. It would make sense in an arbitrary species provided the total weights were positive and the exponential generating function converged to a finite value. Particles at a location.
Couldn't you have just used the letter Z for partition function just to make a few of us happy?
Well, so Mr. But I'm talking to two communities, right? And also Z is wrong for grand partition function anyway. It should be psi, right? So, but Jeeves, grand. Oh, I think I kind of like this. I think I've discovered a new unity. All right. So now here is the expected number of particles at a location is something that would be a direct physical after all, the individual probabilities of particle configurations are going to be incredibly tiny. But the expected number of particles at a point is a kind of index of the density of the gas. So it's a very reasonable thing to look at. And so it turns out that it's expressed by the exponential generating function for connected graphs with root of color p, as we've seen a number of times. Let me not spend a lot of time on that because people have gone through this derivation before. So here's the cluster expansion theorem. Cluster expansion theorem says that if you take these weights to be negative, very strange thing to do, but it's what the physics tells us to do, and take the activities to be positive, and let's suppose we have the Katetsky price condition. So the Katetsky price condition is that the tree exponential generating function is finite at that particular w vector. Then that's an upper bound for the exponential generating function for the expected number of particles at a point. So if you can get the tree thing, which comes from the Katetsky price finite, you can get the thing that you care about finite. This is something you care about in actual physics. It's a much less trivial thing because, remember, it used a bad operation to generate the equation. So that's the famous cluster expansion. Now I'm going to give a sketch of a proof which will have a weakness which I'm afraid I already know who's going to see the weakness, but please, I won't say please be silent, but please consider the virtues of silence. So here's the sketch. After all, we have a closed form expression for the exponential generating function for connected graphs. It's just got this awful scale factor in it. Now, there's a technical thing you can do which is related to the alternating sign property that Alan talked about in his talk. And that's you look at negative of that thing of negative of w, and that's going to turn out to have only positive coefficients in its Taylor expansion. And if you write down the corresponding equation for that, which is a sort of thing that majorizes what you're interested in, you get a plus sign here. I mean, you get the negative of t, which is the absolute value of t. And now this has a lot of virtues. This is an increasing function, so it's a fixed point equation with an increasing function. So you expect that maybe it'll have a solution, which is already nice, but it's a complicated equation. You don't know whether the solution is finite or not. However, once you've convinced yourself that these things have, which you can convince yourself from this equation, that these things have only positive terms in their Taylor series expansion, these guys are increasing functions. So if you look at this thing, you can make things bigger by taking away the scaling, and you just get that. And now the integral is trivial, so you just get that. So basically, you've dominated this type of equation by a tree type equation. So its fixed point should be smaller than the tree fixed point. So that's the proof sketch, and I'm going to pass this slide really quickly before somebody perceptively points out why there's a little bit of extra that you need to say. But
What is the lattice?
oh, the lattice. Okay, good. Yeah. So the lattice I'm considering is I take this complete lattice, the closed interval from 0 to plus infinity, to take functions from the set of colors to that complete lattice. That's also a complete lattice. And if you take a z in this thing, the z is indexed by colors p, which belong to the palette of colors. See, there's a nice palette is the natural combinatorics name for this set, and I guess places might be okay for physics. I don't know.
Some people, abstract
Or polymers, right. Yeah, or polymers for some
But-
people.
But the simplest proof, or at least the proof that I like best, of the alternating sign property uses the Penrose lemma, and the Penrose lemma immediately shows that the bound over connected stuff is, the sum over connected stuff is bounded by the sum
Well,
over trees.
you know, I mean, species theory gives you this fixed point equation, and I'm trying to illustrate how you might use it. There are other ways of doing things. The Penrose identity is actually, in some sense, more subtle in a number of ways.
But do you have some way of using this exact equation without the bound? That would be. Using the integral.
That would be a realization of a fantastic dream. Yeah, you're quite right. Because this bounding thing is very crude. But you would have to use the fact that this t is negative.
Of course.
Yeah.
You always use that.
Yeah, but it would have to somehow get, well, all right. Okay. So it's now 5 o'clock. You people have been very patient. I've given you the first 2 parts of my talk where I tied together everything we've done. Now, of course, I could talk about my own work. So let me do it really like this. And I'd like to end with a kind of last, very humble, very modest tribute to Pierre Leroux. It's namely my list of references.
Already finished?
Thank you.
Bill, can you show us at least how the Fernandez-Procacci result comes out in your context? Above all, because they presented it in what I call level 3.
Everything here is level 1.
Exactly. That's
Yeah.
why I want to see how in your context the Fernandez-Procacci comes out.
Well,
First of all, what is the Fernandez-Procacci condition at level 1? And secondly, what is the proof?
well, the condition is that, so here's this function that they define, which is the same function that they have. And it's
What
conditioned that it has a finite.
So can you remind us what all those things mean?
Can I mean, Fernandez and Procacci, Fernandez had an hour to remind you, and Procacci had an hour to remind you. I only have a minute, and I'd like to try to answer your question the best I can. Can I just say, you undoubtedly very well remember from those previous lectures.
No, I'm just trying to understand your notation.
It's the same. It's the same as it's the same formula that they had with no changes whatsoever.
But they were assuming that you had at most one occupation
Well,
of a site, so you've generalized it.
Well,
somehow.
that's true. There's.
And I want to understand exactly how. What does this say? So
well,
You
this-
have this partition function in the.
It's
partition function, instead of having hardcore, now have.
it's just replacing the hardcore by software.
What do you mean? You have one.
It's the same partition.
You have one particular, in physics language, one particular site P.
Okay, yeah, you have a site P.
And then what?
You have a site P,
Yeah.
then you have a bunch of other sites. From P, you draw these lines with weight absolute value of TPQ. For all these guys, you look at all possible graphs with values TPQ. Or equivalently, you look at the complete graph with a single factor of 1 plus TPQ.
Okay, I'm sorry. So you draw a bunch of lines. You draw as many lines, 0 or more lines, from P to other sites, including multiple lines, or no?
All right. This is the generating function. This is the partition function for all of these guys here except for P. And
So n is how many particles you put on each
So-
site. 1 plus t pair of n is the total Boltzmann weight. for that.
so I look at the usual partition function, grand partition function for all these guys,
Oh, for everybody but P.
everybody but P, and then I look at a factor of P going to all of these guys,
To every,
to all these people. Yeah.
For every site that has a certain number of particles, you put that.
Yeah, if you have 3 particles at a site, you put 3 lines, yeah.
And so n's are, you sum over all occupations of all the sites but p.
Yeah,
N sub p is 0 here in this sum.
P doesn't enter into the sum. Okay, so,
I'm sorry, and then that, one more, and then that, and then you write the corresponding fixed point.
yeah. So it's the same thing, there's a bound and there's a fixed point and so on and so forth. And it improves the, as it's been discussed before, it improves the Katsky-Price result. Now, unfortunately, I don't have a simple species proof of this. I have to use a connected graph identity of the Bridges-Kennedy-Abdussalam-Rivesot type. And I didn't prepare a slide with that identity, but you can get a bound, and then so you now have a kind of tree equation, but it's not a tree equation of the simplest kind, but it's a tree equation where the fibers over every point have some extra have this extra partition function factor. So that's the idea, and then it's the same fixed point story.
Comments?
Yes,
Yeah, Aldo.
I think that also with the Penrose identity, instead of using this.
Well, you proved it with the Penrose identity.
Yes, but also in this level 1 case, it's possible with Penrose identity.
Oh, I believe that. I believe that.
That would be very nice.
I believe that.
It's
Yeah.
Morally the same thing.
I believe that.
With all due respect to Abdussalam Rivesot, Bridges and Kennedy, 3/4 of which are in the audience.
Let me just do this thing. I think that using this bridge formula maybe more interesting. It's more interesting than using the Penrose formula because Bridges Kennedy formula, Bridges Featherfoot are more suitable also for printing attractive potential.
Well, you have a result on that. Yeah. He has a very, very beautiful result where he allows his potentials to be attractive a little bit, but satisfying the stability condition. A gorgeous piece of work. And that uses, in a very essential way, these more subtle identities that we've been discussing. The Rosetta Stone is here by the book.